In this chapter, we will learn imperfections or defects in solids. After studying this chapter, you should be able to do the following. First, describe both vacancy and self-interstitial crystalline defects. Calculate the equilibrium number of vacancies in the material at some specified temperature given the relevant constants. Name the two types of solid solutions and provide a brief written definition of each. Given the masses and atomic weights of two or more elements in the metal alloy, calculate the weight percent and atom percent for each element. For each of the edge, screw, and mixed dislocations, we should be able to describe and make a drawing of the dislocation, note the location of the dislocation line, and indicate the direction along which the dislocation line extends. And also describe the atomic structure within the vicinity of a green boundary. Well, the first question is, why should we study imperfections or defects in solid? Well, if you recall, we have been using or assuming the perfect order exists throughout crystalline structure. But in fact, nothing is perfect, including crystal structures. So imperfections or defects are part of the crystal structure. That's why we need to know it. And also, the properties of some materials are profoundly influenced by the presence of imperfections. Consequently, it is important to have a knowledge about the types of imperfections that exist and the roles they play in affecting the behavior of materials. In fact, some of the impurities and defects are intentionally introduced into the materials to improve the properties of the material. For example, the mechanical properties of pure metals experience significant alternations when the metals are alloyed. Surprisingly, alloying is to introduce impurities or defects into the metal. For example, zinc. If we introduce zinc or add zinc into the copper crystal structure, or zinc is actually one type of impurity atoms or defects. So as a result, the alloy brass, which is the alloy of copper and zinc, is much harder and stronger than pure copper. So we'll learn in the later chapters why the defects can change the mechanical properties of the materials. So, there's really no such thing as a perfect crystal. Crystalline imperfections or defects are always present in materials. So, how do we define crystalline defects? Well, it refers to a lattice irregularity with dimensions on the order of an atomic diameter. So do not mistake the imperfections or defects with flaws of the material. For example, if you break a glass, then you have a crack on a piece of china or ceramic. That crack is not defects. That means it's broken. It's a flaws. Okay. So again, the crystalline defect is on the scale of atomic diameter. So what kinds of crystalline imperfections exist in solids? Classification of crystalline imperfections is frequently made according to the geometry or dimensionality of the defect. Several different imperfections are discussed in this chapter, including point defect. So those associated with one or two atomic positions, and these are zero-dimensional defects. So in the zero-dimensional defects or point defects, we have vacancies, interstitial atoms, or substitutional impurity atoms. And then in the one-dimensional defects, we call that linear defects. We will learn different types of dislocations. And going up in dimension, in 2D, we have interstitial defects. So green boundaries, the boundaries between two grains are called green boundaries. So that's a 2D defect, interstitial defects. Point defects are localized disruptions in otherwise perfect atomic or ionic arrangements in a crystal structure. We have the following types of point defects. The first is vacancy. So you can see here is one atom is missing from the lattice point. So the missing atom will form a vacant or a vacancy. And the second type in opposite to the vacancy is a interstitial atom, where the atom goes into the interstitial site between all the other atoms. So this is the interstitial atom. And the third type is the substitutional atoms. So for example, if we have the lattice arrangement of atom A, but at this point, the atom A is replaced by a different atom, atom B. This will form a substitutional atom. So the atom can be small or smaller than the original lattice, than the original atoms, or it can be bigger. First, let's take a look at point defects in metals. We're talking about pure metals, which means there's only one element and there's only one type of atom. So in pure metals, we can have vacancies and we can have interstitial atoms. So here, interstitial atoms are called self-interstitials because, again, there's only one type of atom. For example, if it's atom A, then we only have atom A, and atom A goes into an interstitial site, so that's why it's called self-interstitials. For vacancies or vacant atomic sites, they are the simplest form of point defects, and where atom is missing from a regular lattice site, a vacancy is created. So this vacancy will cause distortion of planes. We can see from this drawing here indicating the distortion of the regular lattice plane. So if there's no atom or no vacancy, it will be like this. But because one atom is missing, to remain equilibrium, the atoms are kind of going in or shrinking in a little bit, cause the distortion of planes. Self-interstitials means host atoms positioned in interstitial positions between atoms. So it goes into an interstitial site. So we have one extra atom that goes into an interstitial site, but again, all the atoms are the same type of atoms, so it's called self-interstitials. There is no impurity atoms goes into the lattice spaces, so that's self-interstitial. It will also cause a distortion of the planes. A vacancy is when an atom or ion is missing from its normal site in the crystal structures. It is impossible to find a single material without vacancies, so it can be found in all crystalline materials. While some significance of vacancies, it increases entropy and thus increases the thermodynamic stability of crystalline structures, and vacancies are introduced into metals and alloys during solidification is the method to producing metals and alloys at high temperatures or as a consequence of radiation damage. Well, diffusion, which we're going to learn in the next chapter, is only possible because of vacancies. The number of vacancies in the material is not constant. In fact, the vacancy concentration or the equilibrium number of vacancies will increase with temperature. So the relation between the vacancy concentration and the temperature is expressed in this equation, where N sub V is the number of vacancies per volume. It equals to N, which is the number of atoms per volume, times E to the power of negative QV. So QV is the activation energy required to produce 1 mole of vacancies. And QV has the unit of calorie per mole or joules per mole. And this value can be calculated from experimental data. And K is the gas or Boltzmann's constant. So it's a constant. We can choose different values based on the given units of all the other quantities. And T is the temperature. Always express the temperature in Kelvin. So again, vacancy concentration equals to N times E to the power of negative QV over KT. Precisely, vacancy concentration actually is the ratio of number of vacancies per volume over number of atoms per volume, because each atom site can be a potential vacancy site. So this ratio is called the vacancy concentration. So from the previous relation, if we move the N from the right side of the equation to the left, so we get this relation NV over N equals to E to the power of negative QV over KT. And if we plot the vacancy concentration with the temperature K, so this is the relation. Therefore, we say the vacancy concentration increases with temperature and is an exponential dependence. Let's take a look at one example. Find the equilibrium number of vacancies in 1 cubic meter of copper at the given temperature, which is 1000 degrees Celsius. And we know the density, we know the atomic weight of copper, the activation energy Q, and this constant Avogadro's number. Well, first of all, let's write down the equation of number of vacancies as a function of the temperature, and we know that NV equals to N times E to the power of negative QV over K and T. So we're going to use this equation, obviously. Now let's check which quantity we already know and which one we don't know. And first, this is what we're looking for. And then number of atoms per volume. So N is number of atoms per unit volume. And seems like we don't have it directly right now. Let's move on. QV, the activation energy, is given. So this one is given. And K is gas constant or Boltzmann's constant. So we know that value as well. We can use it directly. And temperature, 1000 degrees Celsius, we need to convert it to Kelvin. So we know it as well. T is known. And now we can see the only value we don't know is the number of atoms per volume. Well, let's see, based on the given information, how do we get the number of atoms per volume? So first of all, the values we haven't used are the density, the atomic weight, and the Avogadro's number. Well, if you think about the density rho, the definition will be weight per unit volume. This volume can be cubic meter or cubic centimeter. And if we know this is the definition of density, and we can also say this density actually equals to number of atoms per volume, since that's what we're looking for. So number of atoms per volume times the weight of each volume. So weight of each weight of each atom, and this is N again is number of atoms per volume. So number of atoms per volume times the weight of each atom, we get the weight per volume, right? So now how about what is the weight per atom? Well, we know this atomic weight is the weight of 1 mole of copper, and 1 mole of copper has an A number of atoms. Therefore, the weight of each atom is the atomic weight of the copper divided by the number of atoms per mole. And now we build a relation between the given information rho N and A and NA. Therefore, let's rewrite this equation. Rho density equals to N number of atoms per volume times atomic weight divided by Avogadro's number. And now if we're looking for the number of atoms per volume, we can rewrite this relation where N equals to rho times NA over A. So you can use this relation directly in your calculation later. Now we can write down the solution. So first step is to determine the total number of lattice sites or atoms. So sometimes when you check the textbook, it may say lattice sites. Sometimes it may say the atoms. So, well, for a pure metal, this is the same thing. Number of atoms equals to the number of lattice sites. And use this equation we just derived. N equals to NA times rho over A, and substitute the numbers N with corresponding or correct units. So NA is sites per mole, or actually we should say that's the atoms per mole, and rho gram per cubic centimeter. So if we want to have the unit of, or have the number of atoms per cubic meter, since we are looking for the number of vacancies in per cubic meter, so we need to do the conversion, convert cubic centimeter to cubic meter by multiply this conversion factor and divide it by A, and the value of N is calculated to be 8.0 times 10 to the power of 28 sites per cubic meter. So now we figured out N, and every quantity in this equation are ready to use. And so the second step is to use this relation to determine the equilibrium vacancy concentration NV. We substitute, so in this step I still have this N here as an expression instead of substituting the number N. Substitute the QV activation energy given in the problem, and it's given in unit of electron volt per atom. So based on this given information, we need to choose the corresponding unit for Boltzmann's constants. So we should use this unit, electron volt per atom per Kelvin. So the value, this constant is 8.62 times 10 to the negative 5. Temperature, remember we should not use temperature in centigrade. We should convert it to Kelvin, which is 1273 Kelvin. So this E part is calculated to be 2.7 times 10 to the negative 4. And then times N number of lattice sites, or number of atoms, or number of possible vacancy sites, which we just calculated, and this N equals to 8.0 times 10 to the power of 28 sites per cubic meter. We substitute the number N, and the final answer for equilibrium vacancy concentration NV is 2.2 times 10 to the power of 25 or 25th vacancies per cubic meter. Well, that's actually a huge number. The most familiar metals are not highly pure, rather they are alloys, in which impurity atoms have been added intentionally to impact specific characteristics of the material. So let's take a look at the point defects in alloys. By adding the impurity atoms to the host atom, there are two possible results. One is solid solution, another one is a second phase. So in this chapter, we will focus on solid solution and we will learn second phase later. So solid solution of B in A is the host atom or host material or like the solvent, and B is the solute. So a solid solution forms when the solute atoms are added to the host metal. The result is the crystal structure is maintained and no new structures are formed. In other words, the atoms B or B atoms are randomly distributed throughout the crystal structure of A. So the impurity point defects are found in solid solutions, and there are two types of point defects in solid solutions. One type is called substitutional, another one is called interstitial. So the substitutional solid solution, solute and impurity atoms replace or substitute for the host atoms. For example, copper in nickel. The copper atom will replace the nickel atom at those lattice sites. So the second type is interstitial solid solution. So for interstitial solid solutions, impurity atoms fill in the voids or the interstices among the host atoms. To form substitutional solid solutions, the solvent and the solute atoms should satisfy the Hume rule 3 rules. Rule number 1, the size of the atomic size should be similar. The difference between the atomic radii should be less than 15%. And second, proximity in periodic table, which means those two atoms should have similar electron negativity. And third condition is for pure metals, they should have the same crystal structure. Both are BCC or both are FCC, for example. And the fourth is the valences. So if all else being equal, number 1, 2, 3 are equal, then a metal will have a greater tendency to dissolve a metal of higher valence than one of lower valence. Let's take a look at one example to apply the Hume rule 3 rules to predict the solubility of one type of material in another. So would you predict more aluminum or silver to dissolve in zinc? So we have the data given here with atomic radius, crystal structure, electron negativity, and valences for corresponding elements. First, let's check the atomic radius. Based on the first condition, the atomic radius, the difference between atomic radius should be less than 15%, so they should have similar atomic radii. Well, in this case, both aluminum and silver has larger atomic radii than zinc, but aluminum is smaller than silver, so it's more close to zinc, therefore slightly favors aluminum. And second, let's check the electron negativity. Well, again, they should have similar electron negativities. Again, aluminum is 1.5, which is much closer to zinc than the silver. Therefore, it favors aluminum again. And next factor will be crystal structures. So both aluminum and silver has FCC structures, where zinc has HCP structure. So although they are slightly different, but we know that both FCC and HCP structures are closed packed structures. So now it's a tie. So if we said if all conditions are the same, we need to check valences. Well, now I think aluminum wins, but let's go ahead and check the valences. And higher valence means more soluble. So again, the valences favors aluminum. So that means this suggests aluminum is more soluble in zinc, and this agrees with experimental observations.